Right now, at this very moment, you're living in what geologists call an interglacial period, a warm phase, a brief window of comfortable temperatures that won't last. In about 50,000 years, give or take, Earth will begin freezing again. Massive ice sheets will advance from the poles, grinding continents beneath billions of tons of ice. Sea levels will drop hundreds of feet. And it'll happen not because of some random catastrophe, but because of a pattern that's been repeating like clockwork for the past million years. Every 100,000 years, Earth freezes, then it thaws, then it freezes again. With the regularity of a metronome, our planet swings between ice ages and warm periods. We're living in the warm part right now, but we're late in the cycle. The clock is ticking. If you're using this to fall asleep, that's literally why I make it. So subscribe maybe, and tell me where you are and what time it is. I check comments, and it's fascinating. Tokyo at sunrise, London at lunch, Los Angeles late at night, all listening to the same story about our frozen planet. The last ice age ended 12,000 years ago. 12,000 years. That sounds like forever, right? It's not. In geological terms, it's nothing. A blink. The entire span of recorded human history, every civilization we've ever built, every pyramid, every city, every empire, all of it happened during this current warm period. And warm periods don't last. They never have. Here's what makes this pattern so strange. For most of Earth's history, ice ages didn't follow predictable patterns at all. Sometimes the planet would stay warm for millions of years. Other times it would freeze for even longer. But for the past million years or so, something changed. Earth locked into a rhythm. Freeze for 90,000 years, warm up for 10,000 to 15,000 years. Repeat, over and over again, as regular as breathing. Scientists have known about ice ages since the 1800s. They'd found evidence that glaciers once covered places like New York and London, scratches on bedrock where ice sheets dragged boulders, piles of debris left behind when the ice melted. Strange out-of-place rocks carried hundreds of miles from where they formed. The evidence was undeniable. Earth had been frozen. Recently. But here's what drove scientists crazy for over a century. Why did it happen? Why so regularly? What could possibly cause the entire planet to freeze and thaw on such a precise schedule? Random climate fluctuations couldn't explain it. Random isn't regular. Volcanic eruptions couldn't explain it. They're too unpredictable, too variable in their effects. Even changes in the sun's output couldn't explain it. The sun doesn't dim and brighten on a perfect 100,000-year cycle. For decades, the Ice Age pattern was one of the deepest mysteries in all of Earth science. And the answer, when it finally came, turned out to be stranger and more beautiful than anyone imagined. It wasn't something happening on Earth that caused the pattern. It was something happening to Earth in space. Our planet's relationship with the sun changes over time, not dramatically, not obviously, but in subtle, precise ways that transform our entire climate system. Earth wobbles as it spins. Its orbit stretches and shrinks. The tilt of its axis shifts back and forth. These changes are tiny, almost imperceptible, but they're enough. Enough to determine whether New York City sits under a mile of ice or basks in summer heat. Enough to control whether sea levels rise or fall by hundreds of feet. Enough to make the difference between a frozen planet and the warm world we know today. The story of how scientists discovered this is one of the most remarkable detective stories in the history of science. It took decades of work. Ice cores drilled miles deep into Antarctic glaciers, preserving hundreds of thousands of years of climate history. Ocean sediments pulled from the seafloor containing the fossilized shells of microscopic creatures that recorded ancient temperatures, mathematical calculations tracing the wobbles and shifts in Earth's orbit backward through time. Slowly, piece by piece, the picture came together. Earth's ice ages aren't random. They're not chaos. They're the result of a cosmic dance between our planet and the sun, a gravitational waltz that's been playing out for millions of years. And we've finally learned the choreography. Tonight, we're going to explore that dance. We're going to understand why Earth freezes every 100,000 years. Not just that it happens, but how it happens. The orbital mechanics that trigger it. The feedback loops that amplify it. The tipping points that end it. We're going to see what Earth looked like during the last ice age, with ice sheets 2 miles thick covering continents, with sea levels so low you could walk from Asia to America. And we're going to understand where we are right now in this cycle, why our current warm period is already older than most, what the future holds for our descendants, whether human activity has disrupted the pattern or just postponed the inevitable. The answers involve cosmic mechanics playing out over millions of miles, climate feedbacks cascading through oceans and atmosphere, ice sheets that take 90,000 years to grow, but only 10,000 years to melt. It's a story that spans our entire solar system and explains the world beneath your feet. So, get comfortable. Close your eyes if you want. We're going back. Way back. To when scientists first realized Earth had a frozen past and began asking the question that would take a century to answer. Why does our planet freeze on schedule? For most of human history, we had no idea Earth froze repeatedly. No concept that ice sheets miles thick once covered New York, London, Chicago. That wasn't ancient mythology. That was Tuesday afternoon 20,000 years ago. Our ancestors living through these ice ages didn't know they were in an ice age. To them it was just the world. Cold, harsh, but normal. And when the ice retreated, the people who lived through the warming had no frame of reference to understand what had happened. No written records, no scientific instruments, just oral traditions about a time when the world was different, stories that eventually faded into myth. So for thousands of years of human civilization, we built cities, developed agriculture, invented writing, mathematics, philosophy, all while completely ignorant of the fact that our planet had a pattern, a rhythm, a cycle of freezing and thawing that had been repeating for millions of years. The first hints came in the 1800s. Geologists in Europe started noticing something weird. Scratches on bedrock, grooves carved deep into solid stone, running in consistent directions across entire regions. Boulders sitting in places they had no business being. Rocks that clearly came from hundreds of miles away, just sitting there in the middle of valleys like they'd been dropped from the sky. Then there were the moraines, ridges of jumbled rock and soil forming arc-shaped patterns across landscapes. None of it made sense, until a Swiss geologist named Louis Agassiz proposed something radical in 1837. Those scratches were made by glaciers. Those boulders had been carried by ice sheets. Those moraines mark the edges of ancient glaciers that had once covered half of Europe. People thought he was crazy. The idea that ice sheets could cover entire continents seemed absurd, but Agassiz kept collecting evidence. He showed how modern glaciers in the Alps created exactly the same patterns. The scratches, the transported boulders, the moraines, everything matched. By the 1860s, most scientists had accepted it. Earth had experienced at least one ice age, but they thought it was a one-time event, a single catastrophic period in Earth's distant past. They had no idea they were looking at evidence of the most recent cycle in a pattern that stretched back millions of years. The real breakthrough didn't come until the 1970s and 1980s, and it came from two of the most inhospitable places on Earth, Antarctica and Greenland. Scientists had figured out that ice sheets aren't just frozen water, they're archives, time capsules containing information about ancient climates, preserved in frozen layers that accumulate year after year, century after century, for hundreds of thousands of years. Every winter, snow falls on the ice sheets. Every summer, some of that snow compacts into ice. Year after year, the layers build up like tree rings, creating a vertical timeline stretching down through thousands of feet of ice, and trapped in those layers are tiny air bubbles, pockets of ancient atmosphere preserved exactly as they were when the snow fell. The idea was simple: drill down into the ice sheets, extract cores of ice containing these layers, analyze them to reconstruct what Earth's climate was like when each layer formed. Simple in concept, absolutely brutal in execution. Picture trying to drill a hole 3 kilometers deep into ice in Antarctica, where temperatures regularly drop to -80 degrees Fahrenheit, where storms can appear out of nowhere with winds exceeding 100 miles per hour, where you're more isolated than astronauts in space because at least astronauts can come home in an emergency. Early drilling attempts in the 1950s and 60s barely scratched the surface. The technology didn't exist to drill deep enough or preserve the ice cores without contaminating them. But by the 1970s, engineering had advanced enough to make it possible. Soviet scientists established Vostok Station in the middle of East Antarctica, the coldest place on Earth. American teams set up drilling operations in Greenland. French and Soviet researchers collaborated on projects drilling ever deeper into the ice. In 1985, the Soviet team at Vostok hit a major milestone. They had drilled down over 2,000 meters, reaching ice that was over 150,000 years old. For the first time, scientists could analyze atmospheric conditions from not just the last ice age, but the one before that. And what they found was shocking. The pattern was there, clear as day, locked in the ice, temperature swings following a regular rhythm, cold periods lasting roughly 100,000 years, brief warm periods of 10,000 to 15,000 years, then back to cold, over and over. The data showed at least 2 complete cycles: Ice Age, warm period, Ice Age, warm period, repeating with clockwork regularity. But the Vostok core wasn't the only evidence accumulating. Halfway around the world, other scientists were drilling into the ocean floor, extracting cores of deep-sea sediment. And these sediment cores were revealing something even more extraordinary. See, ocean sediment accumulates incredibly slowly, a few centimeters every 1,000 years, but it accumulates continuously, layer upon layer for millions of years. And buried in those layers are the shells of tiny marine organisms called foraminifera, microscopic creatures that build their shells from calcium carbonate dissolved in seawater. Here's where it gets interesting. The oxygen in those shells comes in 2 varieties, 2 isotopes, normal oxygen-16 and slightly heavier oxygen-18. When ice ages happen and massive amounts of water get locked up in ice sheets, the ocean becomes enriched in the heavier isotope. When the ice melts and that water returns to the ocean, the ratio shifts back. By analyzing the oxygen isotopes in these ancient shells, scientists could reconstruct ocean temperatures going back millions of years. And what they found was staggering. The 100,000-year cycle didn't just go back 150,000 years, it went back over 1,000,000 years, at least 8 major Ice Age cycles in the past 800,000 years, probably more, each one following the same basic pattern: slow descent into cold, 90,000 years of Ice Age conditions, then a rapid warming, 10,000 years of warmth, then the cycle starts again. But here's where it gets even stranger. When they analyse sediments older than about 1 million years, the pattern changed. Before then, the cycles were faster. Ice ages came and went every 41,000 years instead of every 100,000 years. Something happened about 1 million years ago that fundamentally changed how Earth's climate system operates. Scientists call it the Mid-Pleistocene Transition. We still don't fully understand what caused it, but it's there in the data, clear and unmistakable. A shift from 41,000-year cycles to 100,000-year cycles. Like Earth's climate system suddenly changed gears. By the late 1980s and early 1990s, the evidence was overwhelming. Multiple ice cores from Antarctica and Greenland, hundreds of ocean sediment cores from around the world, all telling the same story. Earth has a pattern, a rhythm of ice and warmth that has been repeating for at least 2.5 million years. But discovering the pattern raised a bigger question. Why? What could possibly cause such regular climate swings? The answer to that question had actually been proposed decades earlier by a Serbian mathematician named Milutin Milankovic. In the 1920s, Milankovic was working on a problem that seemed completely theoretical at the time. Earth's orbit around the Sun isn't perfectly circular, it's slightly elliptical, and the tilt of Earth's axis isn't constant. It wobbles slightly over time like a spinning top. Milankovic calculated that these orbital variations should cause regular changes in how much sunlight different parts of Earth receive during different seasons. He proposed that these changes could trigger ice ages. When northern summers receive less sunlight, winter snow doesn't completely melt. It accumulates year after year, eventually forming ice sheets. When orbital conditions shift and summers warm up again, the ice melts. Milankovic even calculated the cycles: 100,000 years for changes in orbital shape, 41,000 years for changes in axial tilt, 23,000 years for the wobble of Earth's axis. Nobody paid much attention at the time. It seemed too theoretical, too astronomical. How could tiny changes in Earth's orbit possibly cause mile-thick ice sheets to form and melt? But when the ice core and sediment data started coming in during the 1970s and 80s, scientists made a stunning discovery. The cycles matched. The 100,000-year pattern, the earlier 41,000-year pattern, even shorter 23,000-year fluctuations within the longer cycles. All of it matched Milankovic's calculations. He'd been right. 50 years before we had the technology to prove it, this Serbian mathematician had figured out that Earth's ice ages are triggered by subtle variations in our planet's orbit. By the 1990s, the Vostok ice core had been drilled down to over 3,600 meters, reaching ice that was over 420,000 years old. 4 complete glacial cycles, each one showing the same pattern: slow cooling, long ice age, rapid warming, brief warm period, then repeat. The data was so clear, so regular, you could practically set your watch by it, except your watch would need to measure time in tens of thousands of years. Then in the 2000s, the European project for ice coring in Antarctica, epochs, drilled even deeper. In 2004, they announced they'd reached ice that was 740,000 years old. By 2008, they had extended the record to 800,000 years. 8 complete glacial cycles now visible in the ice, each one following the same rhythmic pattern. And those air bubbles trapped in the ice, They revealed something that would prove crucial for understanding modern climate change. During ice ages, atmospheric carbon dioxide levels dropped to about 180 parts per million. During warm periods, they rose to about 280 parts per million. The correlation was perfect. When CO2 was low, Earth was cold. When CO2 was high, Earth was warm. This wasn't just interesting scientific trivia. This was proof that greenhouse gases fundamentally control Earth's temperature, change the CO2 levels, change the climate. The ice cores provided the smoking gun linking carbon dioxide to global temperature over hundreds of thousands of years. But perhaps the most unsettling discovery was about timing. The warm periods, the interglacials like the one we're living in now, they're short. Really short. 10,000 to 15,000 years on average. Some lasted only 8,000 years. The current warm period started about 11,700 years ago. We're already past the midpoint of what would normally be expected. The data suggest we're living in a brief moment of warmth between ice ages, a temporary window that has allowed human civilization to flourish. All of recorded history, every city we've built, every agricultural system we've developed, every empire that's risen and fallen, it's all happened during this one warm period, this one 11,700-year break in the ice. The scientists analyzing these ice cores realized something profound. Human civilization exists because we got lucky. We evolved and developed complex societies during one of Earth's rare warm phases. If humans had appeared 30,000 years earlier, we'd have been trying to build civilization under mile-thick ice sheets. Pyramids covered in glaciers, Rome buried under ice. None of it would have been possible. But the ice cores also revealed something more immediate. Within the long glacial cycles, there were shorter, more chaotic fluctuations, periods where temperature swung wildly within just decades or centuries. The Younger Dryas event about 12,800 years ago, when Earth suddenly plunged back into Ice Age conditions for over 1,000 years in the middle of the warming trend. Dansgaard-Oeschger events during the last Ice Age, when temperatures in Greenland jumped by 15 degrees Fahrenheit in less than a decade, then crashed back down just as fast. The climate system wasn't just cyclical. It was capable of rapid, dramatic shifts, tipping points where small changes could trigger massive, abrupt climate swings. This was the stuff of nightmares for climate scientists. It suggested Earth's climate wasn't a stable, predictable system. It was more like a ball balanced on a saddle point, capable of rolling quickly into very different states. By the 2010s, ice core drilling had become almost routine. Teams from multiple countries were extracting cores from both poles. The technology had improved to the point where scientists could measure not just temperature and CO2, but dozens of other chemical signatures, methane levels, dust concentrations, volcanic ash layers, even cosmic ray impacts. Each new core added detail to the picture. But the fundamental pattern remained unchanged. Earth freezes for about 100,000 years, warms for about 10,000 to 15,000 years, then freezes again. It's been doing this for over 1 million years. 8 major cycles that we can see clearly, probably dozens more stretching back into the deeper past, and we're living right now in warm period number 9. The discovery of Earth's frozen timeline revolutionized climate science. It proved that massive climate change is normal for our planet, that ice ages aren't anomalies but the default state, that the warm, stable climate that has allowed human civilization to flourish is actually the unusual condition. It also gave us the tools to understand what causes these changes and what that might mean for our future. Because if Earth has a natural rhythm of freezing and warming, and we now understand what drives that rhythm, We can predict what comes next. We can look at where we are in the cycle and make educated guesses about where we're headed. But before we get to predictions, we need to understand the mechanism. How do tiny changes in Earth's orbit translate into mile-thick ice sheets? What's the trigger that tips Earth from warm to cold and back again? The answer lies in space, in the subtle gravitational dance between Earth, the Sun, and the giant planets of our solar system. So here's the thing about Earth's orbit. It's not stable. Not in the way you probably learned in school, with those nice diagrams showing a perfect ellipse around the Sun, unchanging and eternal. That's a simplification. A useful lie we tell students because the truth is way more complicated. The truth is that Earth wobbles. It stretches. It tilts. Like a drunk dancer trying to keep rhythm with 3 different songs playing at once. And it's these wobbles, these cosmic variations, that have been driving the Ice Age cycle for millions of years. There are 3 main movements, 3 separate orbital variations that combine to create the pattern that freezes our planet every 100,000 years. Scientists call them eccentricity, obliquity, and precession. But forget the fancy names for a second. Let's talk about what's actually happening. First, there's eccentricity. This is the shape of Earth's orbit itself. Right now, if you could somehow view Earth's path around the Sun from above, it would look almost circular. Not perfectly circular, but close. The difference between our closest approach to the Sun and our farthest point is only about 3 million miles. In astronomical terms, that's nothing. But Earth's orbit doesn't stay this circular. Over roughly 100,000 years it stretches. Imagine taking a circular track and gradually pulling it into more of an oval shape. That's what happens to Earth's orbit. At maximum eccentricity, the difference between closest and farthest approach increases to about 11 million miles. Now, 11 million miles sounds like a lot, and it is. But here's what's weird. This change in distance only affects the total amount of solar radiation Earth receives by about 0.2%. That's basically nothing. If eccentricity was the only factor, we'd barely notice. Summers might be slightly warmer when Earth was close to the Sun, winters slightly colder when we were farther away, but not enough to trigger continental ice sheets 2 miles thick. So why does the 100,000-year eccentricity cycle seem to control the Ice Age pattern? We'll get to that. Because the answer involves how eccentricity interacts with the other 2 cycles, and that's where things get really interesting. The second variation is obliquity. This is Earth's axial tilt, the angle between Earth's rotational axis and the plane of its orbit around the Sun. Right now, Earth tilts at about 23.5 degrees. This tilt is why we have seasons. When the northern hemisphere tilts toward the Sun, it's summer in the north and winter in the south. 6 months later, the situation reverses. But here's what most people don't know. That 23.5 degree tilt isn't constant. Earth wobbles on its axis over a period of about 41,000 years. The tilt varies between 22.1 and 24.5 degrees. That might not sound like much, just 2.4 degrees of variation, but the effects are enormous. Think about what tilt actually does. It controls how extreme your seasons are. With higher tilt, summer sunlight hits the northern latitudes at a steeper angle, more directly, creating hotter summers. Winter sunlight comes in at an even more oblique angle, creating colder winters. The difference between summer and winter becomes more extreme. With lower tilt, the opposite happens. Summers become cooler because sunlight hits at a less direct angle. Winters become milder for the same reason. The seasons moderate. The difference between summer and winter shrinks. Now, if you're trying to grow an ice sheet, what do you need? You need snow that falls in winter and doesn't melt in summer. You need cool summers more than you need cold winters, because ice sheets don't grow primarily from freezing, they grow from accumulation. Snow piling up year after year, compressing into ice under its own weight. Cold winters give you lots of snow, but hot summers melt it all away. You end up with no net ice accumulation. Mild winters give you less snow. But cool summers mean more of it survives to the next year. Slowly, gradually, the ice builds up. This is why obliquity matters so much for ice ages. When Earth's tilt is low, summers at high latitudes are cooler. Snow and ice that accumulated during winter doesn't fully melt. Year after year, the ice grows. Glaciers spread. Ice sheets form. When tilt is high, summers are too hot. Even if winters are brutally cold, the summer sun melts the ice. Glaciers retreat. Ice sheets collapse. For much of Earth's history, this 41,000-year obliquity cycle was actually the dominant driver of ice ages. Go back 2 million years, look at the geological record, and you'll find ice ages spacing out every 41,000 years, regular as clockwork. The tilt cycle was in control. But then something changed about 1 million years ago. The ice ages started lasting longer. The 100,000-year eccentricity cycle took over. We'll get to why that happened later. For now, just know that obliquity is still working in the background, still affecting ice accumulation, but it's no longer the primary driver. The third variation is precession. This one's harder to visualize, but stay with me because it's crucial. Earth doesn't just tilt, it wobbles. Like a spinning top that's starting to slow down, Earth's rotational axis traces out a slow circle in space. It takes about 26,000 years for the axis to complete one full wobble. This wobble is called precession. And what it does is change which direction Earth's axis points. Right now, Earth's North Pole points roughly toward Polaris, the North Star. But 13,000 years ago, it pointed in a completely different direction. And 13,000 years from now, it'll point somewhere else entirely. So what? Well, here's where it gets interesting. Precession changes which season happens when Earth is closest to the Sun. Right now, Earth reaches its closest point to the Sun, perihelion, in early January. That's winter in the Northern Hemisphere. So Northern Hemisphere winters are slightly warmer than they would otherwise be, because we're closer to the Sun, and Northern Hemisphere summers are slightly cooler, because we're farther away. But 11,000 years ago, the situation was reversed. Precession had oriented Earth so that perihelion happened in July. Northern Hemisphere summers were hotter because Earth was closer to the Sun. Northern Hemisphere winters were colder because we were farther away. This effect is subtle right now because Earth's orbit is nearly circular. Remember, we're only 3 million miles closer to the Sun at perihelion than at our farthest point. With such a circular orbit, the timing of perihelion doesn't matter much. But when eccentricity is high, when Earth's orbit is stretched into more of an oval, precession becomes critically important. With high eccentricity, the difference between closest and farthest approach increases to 11 million miles. Now, the timing of perihelion makes a huge difference. Imagine Earth's orbit is highly elliptical, and precession has oriented things so that Northern Hemisphere summer happens when Earth is at its farthest point from the Sun. Summer sunlight is already hitting at an angle because of Earth's tilt. But now Earth is also millions of miles farther from the Sun than usual. Summers become dramatically cooler. Add in low obliquity, reducing summer sunshine even more, and you have perfect conditions for ice sheet growth. Snow falls in winter. The cool, distant summer sun can't melt it. Year after year, ice accumulates. Within a few thousand years, glaciers are spreading south from the Arctic. Within 20,000 years, ice sheets cover most of Canada and northern Europe. But here's where the three cycles interact in ways that make the whole system incredibly complex. Precession completes a full wobble every 26,000 years. So even during a period of high eccentricity, the effect of precession flips back and forth. For 13,000 years, northern hemisphere summers might happen when Earth is far from the sun, promoting ice growth. Then precession shifts, and for the next 13,000 years, northern hemisphere summers happen when Earth is close to the sun, promoting ice melt. Meanwhile, obliquity is doing its own thing on a 41,000-year cycle. Sometimes high obliquity and perihelion timing align to create extremely hot summers that melt ice. Sometimes low obliquity and perihelion timing align to create cool summers that allow ice to grow. An eccentricity is working on its 100,000-year cycle, sometimes amplifying the effects of precession and obliquity, sometimes dampening them. The result is chaos, beautiful, mathematical chaos. The three cycles create constructive interference in some periods, where all three align to promote either ice growth or ice melt, and destructive interference in other periods, where the cycles work against each other and conditions moderate. Scientists can calculate exactly how much solar radiation, what they call insolation, reaches any given latitude at any given time based on these three orbital parameters. They can produce graphs showing insolation, variations going back millions of years and forward millions of years into the future. When you look at these graphs, you see complexity, spikes and dips at multiple frequencies. The 26,000-year precession signal, the 41,000-year obliquity signal, the 100,000-year eccentricity signal, plus harmonics and combinations where the cycles interact. But here's the mystery that puzzled scientists for decades. When you look at actual Ice Age data from the geological record, you see a clear pattern. For the past million years, Ice Ages have been dominated by the 100,000-year cycle. Glacial periods last roughly 90,000 years, followed by brief 10,000-year warm periods, then another 90,000-year glaciation. The problem is that eccentricity, the 100,000-year cycle, has the weakest direct effect on climate. It only changes total solar radiation by 0.2%. Obliquity and precession have much stronger direct effects on polar insolation, on the amount of summer sunlight hitting high latitudes where ice sheets form. So why does the weakest cycle control the pattern? This is called the 100,000-year problem. And solving it required understanding not just orbital mechanics, but how ice sheets themselves respond to orbital changes. How small variations in sunlight get amplified through feedback loops involving ice, ocean, and atmosphere. The answer is that eccentricity doesn't directly cause ice ages. What it does is modulate the effects of precession. When eccentricity is low, when Earth's orbit is nearly circular, precession barely matters. The timing of perihelion has minimal effect, because Earth's distance from the Sun hardly changes throughout the year. But when eccentricity is high, when the orbit is stretched into a pronounced ellipse, precession becomes critical. Now the 26,000-year wobble creates dramatic differences in seasonal sunlight. Northern Hemisphere summers can be much cooler or much warmer, depending on whether perihelion happens in July or January. So eccentricity acts like a volume knob for the precession cycle. When eccentricity is high, it turns up the volume on precession's effects. When eccentricity is low, it turns the volume down. This creates a situation where ice sheets can grow slowly over many precession cycles during periods of high eccentricity, accumulating more and more ice as precession periodically creates favorable conditions for ice growth. But they can't easily collapse until eccentricity drops and precession's effects weaken. The result is ice ages that last multiple obliquity cycles, multiple precession cycles, but ultimately pace themselves to the eccentricity cycle. You get 100,000-year glacial interglacial cycles driven primarily by the weakest orbital variation. Think of it like this. Precession is pushing ice sheets back and forth every 26,000 years. Obliquity is pushing them back and forth every 41,000 years. Both cycles create periods favorable for ice growth and periods favorable for ice melt. But eccentricity determines how hard these pushes hit. During high eccentricity, the pushes toward ice growth are strong enough to overcome the pushes toward ice melt. Ice sheets survive the warm phases and grow during cool phases. Over multiple cycles, the ice accumulates to enormous extent. During low eccentricity, the pushes are weaker and more balanced. Ice sheets can't grow as easily during cool phases, and they melt more easily during warm phases. The 100,000-year pattern emerges not because eccentricity directly controls ice, but because it controls how effectively the other cycles can influence ice sheet growth and collapse. It's like three musicians playing together. Precession and obliquity are playing loud instruments, guitars maybe, creating strong rhythms on their own timescales. Eccentricity is playing a bass drum, quieter, slower, but setting the underlying tempo that organizes everything else. When all three align, when the cosmic dance synchronizes, that's when Earth freezes. And when the dance shifts, when the cycles move out of alignment, that's when the ice melts and the world warms. For the past 1,000,000 years, this dance has repeated every 100,000 years. Regular enough to predict, complex enough to surprise, powerful enough to bury continents under ice and then melt them away again. And we're living through one of those brief warm periods right now, the interglacial pause between frozen worlds. But the dance continues, the cycles turn, and eventually, inevitably, Earth will freeze again, unless something changes the rules, something that interrupts the cosmic rhythm that's controlled our planet's climate for millions of years. But we're getting ahead of ourselves. First, you need to understand what actually happens when these orbital cycles align to trigger an ice age. How does a small change in summer sunlight create ice sheets 2 miles thick? That's where things get really wild. So here's where things get really interesting. You've learned about Milankovitch cycles, these subtle wobbles in Earth's orbit and axis that change how sunlight hits our planet. And maybe you're thinking, okay, that makes sense. Less sunlight in summer means more ice. Simple cause and effect. Except there's a problem. A massive problem that confused scientists for decades after Milankovitch first proposed his theory. The actual change in solar radiation from these orbital variations is tiny. We're talking about 0.1%. That's 1/10 of 1% difference in the total amount of sunlight reaching Earth. To put that in perspective, that's roughly equivalent to the variation you'd experience by moving 100 miles north or south. It's the kind of difference you wouldn't even notice if it happened tomorrow. So how does a 0.1% change in sunlight trigger an ice age? How does something so small create ice sheets 2 miles thick covering half of North America? It's like trying to explain how gently tapping a domino can eventually demolish a building. The initial force seems completely inadequate for the final result. The answer is that these tiny orbital changes don't create ice ages directly. They trigger them, and once triggered, Earth's climate system has ways of amplifying that initial small push into something absolutely catastrophic. Think of it like this. You're standing at the top of a snow-covered mountain. You dislodge a single snowball, send it rolling down the slope. That snowball is tiny, maybe weighs a few pounds, but as it rolls, it picks up more snow, gets bigger, heavier, starts moving faster. Soon it's not a snowball anymore. It's the leading edge of an avalanche, gathering momentum, accumulating mass, until thousands of tons of snow are thundering down the mountain with enough force to flatten forests. That's what happens when Milankovitch cycles nudge Earth's climate. They start an avalanche, and the first snowball they dislodge is something called the albedo effect. Albedo is just a fancy word for reflectivity. How much sunlight a surface reflects back into space instead of absorbing it. Dark surfaces like forests and ocean water have low albedo. They absorb most of the sunlight that hits them, which warms them up. Light-coloured surfaces like ice and snow have high albedo. They reflect most sunlight back into space before it can warm anything. Fresh snow reflects about 90% of incoming sunlight. Ocean water reflects only about 6%. That's a 15-fold difference in how much solar energy gets absorbed versus reflected. Now imagine it's 120,000 years ago. Earth's orbit has shifted into a configuration where Northern Hemisphere summers receive slightly less sunlight. Not much less. Just that 0.1% we talked about. But it's enough that winter snowfall in northern Canada doesn't completely melt during the following summer. A thin layer, maybe just a few inches, persists through the warm season. That doesn't sound catastrophic, except now you've got snow on the ground during summer, and that snow is reflecting away 90% of the sunlight that would normally be absorbed by the dark ground underneath, which means less heat, which means even cooler temperatures the following summer, which means even more snow persists, which reflects even more sunlight, which cools things even more. This is a positive feedback loop, not positive in the sense of good, but positive in the sense of self-reinforcing. Each cycle makes the next cycle stronger. The initial 0.1% reduction in summer sunlight gets amplified by the albedo effect into something much more powerful. Scientists estimate the albedo feedback alone can double or triple the cooling effect of the original orbital change. But that's just the beginning. Because once you start accumulating snow year after year, eventually you get ice. And ice is different from snow in one critical way. It flows. When snow accumulates to depths of 100 feet or more, the pressure at the bottom is so intense that ice begins behaving like a very slow-moving fluid. The entire mass starts spreading outward under its own weight, flowing away from the center like honey poured on a table. This is how glaciers form. And once you have glaciers, you've started something that creates its own momentum. A glacier isn't just sitting there reflecting sunlight, it's actively changing the landscape. As it flows outward, scraping across bedrock, it grinds rock into powder. That powder, called glacial flour, gets blown by winds and deposited across vast areas. This dust has its own albedo effect, lightening the landscape, causing even more solar reflection. The glacier also creates its own weather. The massive ice sheet is so cold that it generates high-pressure systems above it. These high-pressure zones deflect storm tracks, pushing warm, moist air away and preventing the precipitation that might help melt the ice. The glacier literally creates weather patterns that protect it from melting. But the most powerful feedback mechanism isn't the ice itself, it's what the ice does to Earth's atmosphere. When an ice age begins, global temperatures drop, and when temperatures drop, something crucial happens. Carbon dioxide and methane, the two most important greenhouse gases, get removed from the atmosphere. The mechanism for this is complex. Colder oceans can dissolve more CO2 from the atmosphere. Changes in ocean circulation affect how much CO2 gets locked away in deep water. Wetlands, which produce methane, shrink as water freezes. Permafrost expands, trapping organic material that would otherwise decompose and release greenhouse gases. The net result is that CO2 levels during ice ages drop from about 280 parts per million to around 180 parts per million. Methane drops even more dramatically, and this is huge. These greenhouse gases were helping trap heat in Earth's atmosphere. When they're removed, the planet's ability to retain heat drops significantly. Scientists calculate that this greenhouse gas feedback amplifies the cooling by about 40%. So now your initial 0.1% change in solar radiation has been amplified by albedo effects, then amplified again by greenhouse gas reductions. That tiny orbital nudge has been multiplied into something powerful enough to freeze continents. But wait, there's more. Because the ocean isn't just sitting there passively responding to temperature changes, it's actively participating in the climate transformation through changes in circulation patterns. The ocean moves heat around the planet through a global conveyor belt of currents. Warm water flows near the surface from the tropics toward the poles. When it reaches cold regions, it cools down, becomes denser, and sinks into the deep ocean. This deep water then flows back toward the tropics, completing the cycle. This system is called the Atlantic Meridional Overturning Circulation, or AMOC, and it's one of the most important heat distribution mechanisms on Earth. The Gulf Stream, which keeps Europe much warmer than it would otherwise be, is part of this system. During the transition into an ice age, the AMOC weakens dramatically. Here's why. As glaciers grow, they start dumping fresh water into the North Atlantic. This comes from melting at their edges, from rivers that get dammed by ice and overflow into the ocean, from icebergs breaking off and drifting south. Freshwater is less dense than salt water, so it doesn't sink as easily. This disrupts the whole conveyor belt system. When the AMOC weakens, less heat gets transported from the tropics to the northern regions, which means those regions get even colder, which means glaciers grow even faster, which means more fresh water gets dumped into the ocean, which weakens the AMOC even more. Another feedback loop, another way that a small initial change gets amplified into something enormous. And all of these feedbacks are happening simultaneously. Ice is spreading, albedo's increasing, greenhouse gases are dropping, ocean circulation is changing. Each amplification feeds into the others, creating a cascade of changes that transforms the entire planet. But here's what's really critical to understand. Not all parts of Earth's orbit are equally important for triggering these feedbacks. Scientists discovered that one specific factor matters more than all the others. Northern Hemisphere summer insolation. The amount of sunlight hitting the northern continents during summer. Why is this so important? Because that's where the ice sheets grow. In the southern hemisphere, there's not much land at the right latitudes. Antarctica is already covered in ice year-round. The oceans dominate southern latitudes, and water doesn't accumulate into ice sheets the same way land does. You can freeze seawater, but sea ice doesn't build up into mile-thick glaciers. It stays relatively thin, and it melts easily when conditions change. But in the northern hemisphere, you've got massive continents at exactly the right latitudes for ice sheet formation. Canada, Scandinavia, Siberia. Vast areas of land where snow can accumulate, compress into ice, and build into enormous glaciers. And the critical question isn't how cold winter gets. Winter is already cold enough to produce snow at these latitudes. The critical question is whether that snow melts during the following summer. That's what determines whether ice sheets can begin forming. When Northern Hemisphere summers are warm, all the winter snow melts. Ice ages can't start. When Northern Hemisphere summers are cool, even just slightly cool, snow persists. And once it starts persisting, all those feedback mechanisms kick in. This is why the 100,000-year eccentricity cycle matters so much. It's not that eccentricity directly causes much cooling, it's that eccentricity modulates the effect of precession. When eccentricity is high, precession can create larger differences in summer sunlight. When Earth is also tilted at a low angle, obliquity contributes less summer warming. Get all three cycles aligned just wrong, and Northern Hemisphere summers receive noticeably less sunlight. That's the trigger. And once pulled, the feedbacks take over. The transition into an ice age happens slowly at first. Those first centuries, maybe even the first few thousand years, you might not notice much difference. Snow persists a bit longer into summer in northern regions. Glaciers in mountain valleys start expanding. Average temperatures drop, but only by a degree or two. But the feedbacks are building. Each year the ice spreads a little further. Each year more sunlight gets reflected into space. Each year greenhouse gas levels drop a bit more. And these changes are cumulative. They add up, compound, accelerate. By 10,000 years into the transition, things are clearly wrong. Glaciers that covered a few thousand square miles now cover hundreds of thousands. Northern Canada is disappearing under ice. Scandinavia is being buried. Global temperatures have dropped 5 degrees Celsius. That might not sound like much, but it's the difference between the world you know and a planet where New York City is under a mile of ice. By 20,000 years in, the feedbacks are running at full strength. The Laurentide ice sheet covers most of Canada and extends south past the Great Lakes. The Scandinavian ice sheet buries northern Europe. Sea levels have dropped 400 feet as ocean water gets locked up in ice. Global temperatures are 8 degrees below modern levels. And here's the really terrifying part. Once these feedbacks are fully engaged, the system develops momentum. Even if the orbital conditions that triggered the ice age start to shift back, the ice doesn't immediately melt. It's become self-sustaining. The massive ice sheets create their own weather patterns. The reduced greenhouse gases keep temperatures low. The changed ocean circulation maintains the cooling. This is what scientists call a climate tipping point, a threshold beyond which the system doesn't easily return to its original state. You need a strong push in the opposite direction to reverse the process, and that push needs to be stronger than the original trigger, because now you're fighting against all those feedback mechanisms that have built up. Think of it like pushing a boulder up a hill versus letting it roll down. Getting the boulder to the top requires sustained effort, but once it crests the summit and starts rolling down the other side, it goes on its own, accelerating harder and harder to stop. Earth's climate system has multiple stable states. The warm interglacial state we're living in right now is one stable configuration. Full ice age conditions represent another stable configuration. In between these states are thresholds, tipping points that, once crossed, commit the system to completing the transition. The genius of Milankovitch's insight was recognizing that you don't need a massive force to shift between these states. You just need to push the system past its tipping point. Those tiny orbital variations are just barely enough to do that. They nudge summer temperatures down by a fraction of a degree, That fraction is enough to start snow persisting through summer, and once that happens, Earth's own feedback mechanisms take over and do the rest of the work. But here's where things get really interesting. The transition out of ice ages works differently, much faster. While building an ice age takes 80,000 to 90,000 years of gradual accumulation, ending one can happen in less than 10,000 years, sometimes even faster. This asymmetry exists because the feedback mechanisms don't work the same way in reverse. When orbital conditions shift to increase northern hemisphere summer sunlight, ice starts melting. But ice doesn't amplify warming the same way it amplified cooling. When ice melts, it reveals darker land underneath, which absorbs more sunlight and creates warming feedback. But this happens quickly, all at once, as soon as the ice is gone. Greenhouse gases return to the atmosphere rapidly when the oceans warm. Unlike the slow removal process during cooling, the release of CO2 and methane during warming happens fast. Wetlands expand quickly. Ocean circulation can shift in just a few centuries. It's like the difference between slowly filling a dam versus suddenly breaking it. The build-up is gradual, but the release is explosive. So small changes create massive ice sheets through a cascade of amplifying feedbacks, each multiplying the effect of the original orbital trigger. The 0.1% change in sunlight becomes a 10-degree change in global temperature. A slight shift in Earth's wobble becomes miles of ice. Feedback mechanisms transform a whisper into a roar. And the most unsettling part? These mechanisms are still operating. They're not ancient history. They're fundamental properties of how Earth's climate system works. The feedbacks that triggered ice ages in the past are still present, still waiting. All they need is the right orbital configuration to push Earth past that tipping point again. Which raises an obvious question. Where are we now in this cycle, and when will it happen next? So we've talked about why ice ages happen, how orbital mechanics trigger them, and the complex feedback systems that amplify those initial changes. But here's what you're probably really wondering. What did it actually look like? What was Earth like when ice ruled half the planet? Picture this. It's 20,000 years ago. The last glacial maximum. The coldest, iciest point of the most recent ice age. You're standing somewhere in what will one day be called New York City. Except there is no city. There's no harbour. There isn't even an ocean visible on the horizon. Instead, you're standing at the base of an ice sheet. And when I say ice sheet, I don't mean a frozen lake or even a glacier you might see in Alaska today. I mean a wall of ice that rises above you like a frozen mountain range, 2 miles thick. That's 10,560 feet of solid ice, stacked up, pressing down with so much weight that it's actually deforming the Earth's crust beneath it. The Laurentide ice sheet. That's what geologists call it. At its maximum extent, it covered essentially all of Canada, stretched down into what's now the northern United States, and contained enough water to lower global sea levels by 400 feet. To put that in perspective, if you could somehow melt the entire ice sheet instantly, the resulting water would be enough to flood every coastal city on Earth multiple times over. But you can't see the top of the ice sheet from where you're standing. It stretches beyond the horizon, a wall of white and blue ice that seems to reach into the clouds. Because it does reach into the clouds, at 2 miles high, the top of the ice sheet is actually creating its own weather systems. Cold air flows down off its surface like a perpetual avalanche, creating winds that scream across the frozen landscape at speeds that would ground modern aircraft. The air temperature is brutal. Global average temperatures during the last glacial maximum were 5 to 10 degrees Celsius colder than today. but averages don't tell the whole story. Here, at the edge of the ice sheet, winter temperatures regularly drop to -40, -50 degrees Celsius. That's cold enough that your breath freezes before it leaves your mouth, cold enough that exposed skin freezes in minutes, cold enough that even thinking becomes difficult as your body desperately tries to keep your core temperature up. But the Laurentide ice sheet isn't alone. Across the Atlantic, the Fennoscandian ice sheet covers all of Scandinavia, most of Britain, and large parts of northern Europe. It's slightly smaller than its North American cousin, but still massive enough to bury mountains, fill valleys, and turn entire regions into frozen wastelands. In Asia, smaller ice sheets cover the Himalayas and other mountain ranges, while alpine glaciers extend far lower than they do today. Even in the southern hemisphere, ice sheets expand dramatically. Antarctica grows larger, and glaciers appear in places that are now temperate rainforests. All told, ice sheets and glaciers cover about 30% of Earth's land surface during glacial maximum. Today, they cover about 10%. That means ice has claimed an additional 11 million square miles of territory. That's roughly equivalent to covering the entire continent of Africa in ice 2 miles thick. But here's what makes it even more dramatic. All that water had to come from somewhere. The ice sheets aren't made of magical frozen air. They're made of water, water that evaporated from the oceans, fell as snow on the ice sheets, and never made it back to the sea. For 80,000 years, this one-way journey of water from ocean to ice sheet has been slowly draining the world's seas. By 20,000 years ago, sea levels are 400 feet lower than they are today. 400 feet. That's taller than a 40-story building. Coastlines are completely unrecognizable. The ocean has retreated so far that enormous areas of continental shelf are now dry land. In Southeast Asia, the islands of Indonesia, Malaysia and the Philippines are all connected to mainland Asia by a massive landmass called Sunderland. You could walk from Vietnam to Borneo without getting your feet wet. In the Mediterranean, islands like Sicily and Malta are connected to Italy and North Africa. The British Isles are part of mainland Europe, connected by a broad plain that will later become the English Channel. But the most consequential land bridge is in the far north, connecting Asia to North America. The Bering Land Bridge, or Beringia as scientists call it. At its maximum extent, it's not really a bridge at all. It's more like a subcontinent, stretching 1,000 miles from north to south, covering an area larger than Texas. And it's across this bridge that humans make one of the most important journeys in our species' history. Small groups of hunters, following migrating herds of animals, gradually work their way across Beringia from Asia into North America. They have no idea they're discovering a new continent. They're just following food, moving with the seasons, doing what their people have done for thousands of generations. But this time, they keep going. And eventually, they find corridors between the ice sheets, narrow, ice-free passages that lead south into the heart of North America. Within just a few thousand years, their descendants will have spread from Alaska to the tip of South America, colonizing 2 entire continents that had never seen human footprints before. All because sea levels dropped 400 feet and created a frozen highway between worlds. But let's go back to that ice sheet margin where we started, because something interesting is happening at ground level. Despite the brutal cold, despite the wall of ice dominating the horizon, this place isn't dead. It's not some sterile frozen wasteland. It's actually teeming with life. The ground beneath your feet isn't solid ice, it's tundra, frozen for most of the year but thawing slightly in summer. Tough grasses and low shrubs have adapted to survive here, plants that can photosynthesize in near-freezing temperatures and complete their entire reproductive cycle in the few weeks of summer warmth. And where there are plants, there are herbivores. You hear them before you see them. A deep rumbling sound that you feel in your chest, like distant thunder that won't stop. Then they appear on the horizon. Woolly mammoths, not just one or two. A herd of perhaps 30 individuals moving slowly across the tundra, their curved tusks swinging as they use them to sweep snow aside and reach the vegetation beneath. They're enormous. Bulls can stand 11 feet tall at the shoulder and weigh 6 tons. But their size isn't their most impressive feature. It's their adaptation to the cold. That shaggy coat isn't just for show. It's a sophisticated insulation system, with long guard hairs up to 3 feet long covering a dense underlayer of fine wool. Beneath the fur, a layer of fat up to 4 inches thick provides additional insulation. Their ears are tiny compared to modern elephants, reducing heat loss. Their trunk has specially adapted blood vessels that warm cold air before it reaches their lungs. These animals aren't just surviving the Ice Age, they're thriving in it. Mammoths have been evolving in cold climates for hundreds of thousands of years, and by 20,000 years ago, they've become perfectly adapted to life at the edge of the ice. They can survive on tough, low-quality vegetation that other herbivores can't digest. They can smell water sources buried under feet of snow. They can navigate by memory across vast, featureless landscapes using mental maps passed down through generations. But mammoths aren't alone out here. Following the herd at a distance, you spot the predators. A pack of dire wolves, each one significantly larger than modern grey wolves, weighing up to 150 pounds. They're not hunting the adult mammoths. That would be suicide. But they're watching for the weak, the sick, the young. Any mammoth that shows vulnerability becomes a target. Further away, you catch a glimpse of something that makes even the dire wolves nervous. A saber-toothed cat. Smilodon. This isn't the sleek, agile predator you might imagine. It's built like a linebacker, weighing up to 600 pounds, with massive forearms designed for wrestling prey to the ground. And those famous fangs, up to 7 inches long, are precision killing instruments, evolved to pierce the thick hide and fat layers of Ice Age megafauna. This is the world of the Ice Age. Not an empty frozen desert, but a harsh, competitive ecosystem where everything is bigger, tougher, and more dangerous than its modern equivalents. Giant ground sloths the size of elephants, glyptodons, basically armoured mammals that look like Volkswagen Beetles with tails, cave bears twice the size of modern grizzlies, short-faced bears even larger, possibly the largest mammalian predators that ever lived on land. All of these creatures are products of the same selective pressures. In cold climates, Bergmann's rule kicks in. Larger body size means better heat retention. Animals that can grow bigger have a survival advantage. So over hundreds of thousands of years, many Ice Age species have become giants. But here's the thing about the Ice Age world. It's not uniform. While the ice sheet margins support tundra ecosystems like the one we're standing in, much of the planet looks completely different. Travel south, away from the ice sheets, and you find something unexpected. The world is drier, much drier. With so much water locked up in ice sheets, there's less moisture in the atmosphere, less water vapour to form clouds and rain. The hydrological cycle, that endless loop of evaporation and precipitation that regulates Earth's climate, has been dramatically slowed down. The result is expansion of deserts and grasslands on a massive scale. The Sahara Desert extends much further south than it does today. The Amazon rainforest, that vast green lung of the planet, shrinks dramatically, replaced in many areas by savanna and grassland. Australia's deserts expand to cover even more of the continent. But it's the grasslands that really define Ice Age geography. Vast prairies and steppes stretch across the continents, supporting enormous herds of grazing animals. The Mammoth Steppe, as it's now called, extended from Spain all the way across Europe and Asia to North America, forming the largest biome in Earth's history. Millions of square miles of cold-adapted grassland supporting billions of herbivores and the predators that followed them. These weren't the lush grasslands you might imagine in Africa today. Ice Age grass was tough, low-growing, nutrient-poor. But there was a lot of it, and the animals that could digest it efficiently had access to essentially unlimited food. The Mammoth Steppe supported population densities of large herbivores that were probably higher than anywhere on Earth today. Imagine the Serengeti migration, but spread across an area 20 times larger and lasting 100,000 years. Yet even in this harsh, cold, dry world, there were refuges, places where local geography created microclimates that preserved warmer, wetter conditions even during glacial maximum. These refugia, as biologists call them, were crucial for survival of species that couldn't adapt to Ice Age conditions. In southern Europe, areas around the Mediterranean retained relatively mild climates. In North America, ice-free areas along the Pacific coast provided refuge for temperate forests. In Asia, river valleys and coastal regions preserved pockets of warmer habitat. And in these refugia, species that couldn't survive in the Ice Age world waited out the cold periods, maintaining small populations that would explode and spread when the ice finally retreated. For humans, these refugia were critical. While our ancestors were behaviorally capable of surviving in Ice Age conditions, we still preferred warmer climates. Archaeological evidence shows that during glacial maximum, human populations concentrated in these refuge areas. Southern Spain and Portugal, the Italian and Balkan peninsulas, the Middle East, coastal China, southern Africa. In these relatively hospitable regions, human populations remained stable or even grew. During the worst of the Ice Age, they developed specialized technologies for exploiting local resources. They created art, engaged in trade, refined their social structures, and when the ice finally began to retreat, they were ready to expand and repopulate the regions that had been locked under ice for millennia. But life in these refugia wasn't easy. Even in the warmest Ice Age refuges, temperatures were still several degrees colder than today. Resources were more limited, concentrated in smaller areas, leading to increased competition both between human groups and with other species trying to survive in the same places. This compression, this forcing of multiple species into smaller viable territories, created intense evolutionary pressure. Species that couldn't adapt went extinct. Those that could became highly specialized, perfectly tuned to their specific refuge environments. And when the ice retreated, and these populations expanded back into newly available territories, they brought these specialized adaptations with them, adaptations that had been forged in the crucible of Ice Age survival. By 20,000 years ago, Earth was a planet divided. In the far north and south, ice sheets miles thick. At the ice margins, tundra supporting herds of mammoths and other cold-adapted megafauna. In the mid-latitudes, vast grasslands and expanded deserts, and scattered throughout small refugia where forests, wetlands, and more diverse ecosystems persisted. Connecting it all, newly exposed land bridges allowed species to migrate between continents that are now separated by oceans. Animals, plants, and humans spread across these bridges, mixing populations that had been isolated for tens of thousands of years, creating new communities and new evolutionary possibilities. This was the world that would persist until around 11,700 years ago, when the most recent ice age finally ended. For 100,000 years, this had been the normal state of Earth. Ice-dominated, cold, dry, harsh. The warm periods between ice ages, periods like the one we're living in now, those were actually the exceptions. Brief interludes when the ice retreated and the planet briefly remembered what warmth felt like. But those interludes, however brief, were about to change everything. Because during the next warm period, something unprecedented was going to happen. One species, humans, would develop agriculture, cities, and civilization, and they would do it so quickly that by the time the next ice age was scheduled to arrive, they would be capable of altering the climate themselves. But we're getting ahead of ourselves. First, we need to understand how ice ages end, because the process of deglaciation, of melting 2 miles of ice and raising sea levels by 400 feet, that story is just as dramatic as the freeze, and it happens much, much faster than anyone would expect. Because here's the thing about ice ages, they're patient. They build slowly, methodically, layer by layer, spreading across continents over tens of thousands of years. The ice advances incrementally, grinding forward at the pace of human hair growth, carving valleys and pushing continental margins southward, generation after generation. But when they end, they don't just fade away gradually. They collapse. They die violently, dramatically, faster than anything you might imagine. An ice age that took 90,000 years to build can vanish in 5,000 to 10,000 years, sometimes even faster. That's like spending a month carefully constructing a sandcastle, grain by grain, only to watch the tide destroy it in minutes. Except the sandcastle is 2 miles thick and covers entire continents, and the tide is a cascade of feedback loops that turns Earth's climate system into something resembling a runaway train. This asymmetry, this strange imbalance between glacial advance and glacial retreat, puzzled scientists for decades. Why would ice ages end so much faster than they begin? The answer, it turns out, reveals one of the most fascinating and terrifying aspects of Earth's climate system, the power of positive feedback loops. Let's start with the trigger. Remember those orbital variations we talked about, the Milankovitch cycles that set this whole process in motion. During an ice age, Earth's orbit and axial tilt are configured in ways that minimize summer heating in the northern hemisphere. The ice sheets grow because summer never gets warm enough to melt the previous winter's snow. But the orbital dance never stops. Eventually, inevitably, the configuration begins to change. The obliquity increases, tilting the northern hemisphere more directly toward the sun during summer. The precession shifts, aligning northern hemisphere summer with Earth's closest approach to the sun. The eccentricity increases, making that closest approach even more significant. These changes happen gradually, just like the changes that initiated the Ice Age. But their effects are asymmetric, because once warming begins, Earth's climate doesn't just respond linearly, it amplifies. Think of it like pushing a boulder uphill versus watching it roll down. Getting that boulder to the top requires constant, sustained effort. Gravity works against you every inch of the way. But once you get it over the peak, even a tiny push sends it accelerating downward, gaining momentum with every foot it falls. The warming that ends an ice age is that boulder going downhill. And the slope is steep. The first feedback loop involves something that's been locked away for tens of thousands of years: carbon dioxide. During ice ages, the oceans get cold, really cold, and cold water can hold more dissolved gas than warm water. This is basic chemistry, the same reason your soda goes flat faster when it's warm. As the ice age progresses, the oceans absorb enormous amounts of CO2 from the atmosphere. Not just a little, we're talking about reductions of nearly 100 parts per million. The carbon gets pulled down into the deep ocean where it's sequestered, locked away in the cold, dark depths for millennia. But when orbital forcing begins to warm the planet, the oceans start warming too, and warm water can't hold as much dissolved gas. So the CO2 comes back out, all of it. The carbon that's been locked away starts bubbling back into the atmosphere, and CO2, as we all know by now, is a greenhouse gas. It traps heat. The more CO2 enters the atmosphere, the more heat gets trapped. The more heat gets trapped, the warmer the oceans get. The warmer the oceans get, the more CO2 they release. It's a self-reinforcing cycle, a feedback loop that amplifies the initial warming from orbital forcing by a factor of 2 or 3 or even more. But the CO2 release is just the beginning. The really explosive feedback comes from something that's been frozen for the entire ice age: methane. Now, methane is a greenhouse gas on steroids. Molecule for molecule, it's roughly 25 times more effective at trapping heat than CO2 over a century-long timescale. And during ice ages, vast quantities of methane are locked up in two places: permafrost and methane clathrates. The permafrost is straightforward. It's frozen soil, extending hundreds or thousands of feet deep across enormous swathes of northern Asia and North America. Within this frozen ground, dead organic matter from tens of thousands of years has been preserved, locked in ice like a time capsule. When the warming begins and the permafrost starts to thaw, microbes wake up and begin decomposing all that ancient organic matter, and when they do, they produce methane. Lots of it. The methane escapes into the atmosphere, trapping more heat, which causes more permafrost to thaw, which releases more methane. Another feedback loop, accelerating the warming. Methane clathrates are even more dramatic. These are cage-like structures of ice that form under high pressure in ocean sediments and beneath ice sheets. They trap methane molecules in a kind of frozen prison. During ice ages, massive deposits of these clathrates build up on continental shelves and beneath the ice. They're stable as long as conditions remain cold and pressure remains high. But when warming begins, especially in the oceans, these deposits become unstable. The ice cages begin to break down. When they do, the methane doesn't seep out gradually. It can be released in massive bursts, geological events that pump enormous quantities of greenhouse gas into the atmosphere within decades or centuries. Some scientists think these methane releases might be one reason why deglaciation can happen so catastrophically fast. Once you trigger large-scale clathrate collapse, you've essentially lit a fuse on a climate bomb. The warming becomes self-sustaining, independent of the orbital forcing that initiated it. Then there's the albedo feedback, and this one's beautifully simple. Ice is white. White surfaces reflect sunlight back into space. This is why you wear light colours in summer. The light doesn't absorb as much heat. During an ice age, Earth is covered in reflective white ice sheets that bounce solar radiation back into space before it can warm the planet. But as the ice begins to melt, it exposes darker surfaces underneath. Dark soil, dark rock, dark ocean water. These surfaces absorb heat instead of reflecting it. The absorbed heat causes more melting. The more melting exposes more dark surface. More dark surface means more heat absorption. More heat absorption causes more melting. You see where this is going. It's another feedback loop, another amplifier that turns gentle orbital warming into rapid deglaciation. But the really dramatic part, the thing that makes Ice Age endings genuinely catastrophic, is what happens to the ice sheets themselves. For tens of thousands of years, these massive glaciers have been stable, balanced between accumulation in their interiors and melting at their edges. Their dynamic systems constantly moving, but in equilibrium. Then the warming begins. At first, the changes are subtle. A bit more melting at the southern margins, some thinning at the edges, but ice sheet physics includes something called the marine ice sheet instability hypothesis. And this is where things get properly terrifying. Many ice sheets, particularly the ones that covered North America and Europe during the last ice age, extended far enough that their edges were resting on seafloor that was below sea level. As the ice sheet grows and pushes outward, it can remain stable even in these marine environments as long as it stays thick and cold. But if warming causes the ice sheet to start thinning, or if sea level begins to rise from melting elsewhere, water can penetrate underneath the ice, and water is warmer than ice. It melts the ice from below. Once this process starts, it can trigger a catastrophic collapse. The ice sheet doesn't just melt from the edges inward, it destabilizes, massive chunks break off. The interior of the ice sheet, no longer supported by its edges, begins flowing faster toward the sea. The flow causes more thinning. More thinning allows more warm water underneath. More warm water causes more melting from below. Within centuries, ice sheets that were thousands of feet thick can effectively disintegrate. This process has left its signature all over the geological record. They're called meltwater pulse events, and they're exactly as dramatic as they sound. During these pulses, catastrophic amounts of ice collapse into the oceans within a few centuries. Sea levels rise 10, 15, sometimes 20 feet in the span of time between your birth and your grandchildren's adulthood. Coastal regions that had been inhabited for thousands of years suddenly flood. River valleys that had served as migration corridors become drowned estuaries. Islands disappear. The archaeological record from these periods shows abrupt abandonments of coastal sites, evidence of human populations forced to flee rising waters that probably seem to advance generation by generation like an unstoppable tide. But perhaps the strangest twist in this story of rapid deglaciation is what happened 12,800 years ago. The last ice age was in full retreat. CO2 was rising, methane was being released, ice sheets were collapsing. Global temperatures had been climbing steadily for several thousand years. Then suddenly, abruptly, the warming stopped. Global temperatures plunged back toward Ice Age conditions. In some regions, the change happened within a single decade. In Greenland, ice core records show temperature drops of 15 degrees Fahrenheit in less than 10 years. This cold snap, called the Younger Dryas, lasted for more than 1,000 years before warming resumed as suddenly as it had stopped. What happened? The most widely accepted explanation involves one of those catastrophic meltwater pulses. As the massive Laurentide ice sheet over North America collapsed, it created enormous glacial lakes dammed by ice. Lake Agassiz at its peak contained more water than all modern Great Lakes combined. For thousands of years, this lake drained south into the Gulf of Mexico. But around 12,800 years ago, something changed. The ice dam broke or shifted, and the entire lake, thousands of cubic miles of fresh water, suddenly drained northeast into the North Atlantic. This wasn't a gradual process. It was a flood of biblical proportions, possibly discharging more water than all Earth's rivers combined, sustained for months or years. and it had a dramatic effect on ocean circulation. The North Atlantic meridional overturning circulation, the system that includes the Gulf Stream, depends on the sinking of cold, salty water in the far North Atlantic. This sinking drives the entire conveyor belt that redistributes heat around the planet. But the Gulf Stream system is sensitive to salinity. It only works if the water is salty enough to sink. When Lake Agassiz dumped thousands of cubic miles of fresh water into the North Atlantic, it was like throwing a wrench into the machinery. The surface waters became too fresh to sink. The circulation system slowed or possibly shut down entirely. Without the Gulf Stream bringing warm water north, temperatures across the northern hemisphere plummeted. Europe, which had been warming steadily, suddenly experienced near glacial conditions again. The ice sheets that had been retreating began advancing. In some regions, glaciers reoccupied valleys they had only recently abandoned. For more than 1,000 years this cold snap persisted. Then, just as suddenly as it began, it ended. The North Atlantic circulation system recovered, possibly because enough fresh water had either evaporated or been mixed into the deep ocean that salinity returned to normal. The warming resumed, even more rapid than before. Within decades, temperatures shot back up to interglacial levels. The ice sheets resumed their collapse, and this time nothing stopped them. By 11,000 years ago, the great ice sheets were essentially gone. The Ice Age was over. Earth had transitioned into the Holocene, the interglacial period we still inhabit today. What the younger Dryas taught us is that even during rapid warming, the climate system can be knocked off course by catastrophic events. The transition from glacial to interglacial isn't smooth. It's punctuated by sudden reversals, regional variations, events that must have seemed absolutely apocalyptic to the humans living through them. Imagine your ancestors watching the world warm for generations, seeing forest replace tundra, watching ice retreat year after year. Then suddenly, within a single lifetime, the cold returns. The ice advances again. Everything reverses. Then 1,000 years later, your descendants watch it reverse again, even faster. That's not just climate change, that's climate chaos, driven by feedback loops and tipping points that amplify small changes into enormous transformations. And all of this, the CO2 release, the methane bombs, the ice sheet collapse, the meltwater pulses, the ocean circulation changes, all of it happens faster than the gradual orbital forcing that initiated it. Because once you start pushing that boulder downhill, momentum takes over. Earth's climate system, when forced out of equilibrium, doesn't return to equilibrium gently. It lurches, jumps, crashes from one stable state to another. Ice ages end fast because warming triggers feedback loops that amplify themselves. And once those loops engage, once the ice starts melting and the greenhouse gases start releasing, and the dark surfaces start absorbing heat, there's no stopping it. The Ice Age doesn't fade, it collapses, usually within 10,000 years, sometimes within 5,000. Occasionally, in the span of centuries, the world transforms from frozen wasteland to temperate paradise. Your great-great-grandfather is hunting caribou on ice sheets. You're farming in river valleys. That's how fast ice ages can end. That's the power of positive feedback in Earth's climate system. And that's why, when you look at the geological record, the transitions from glacial to interglacial show up as sharp vertical lines, while the transitions from interglacial to glacial show up as long, gradual slopes. The descent into cold is slow and steady. The emergence into warmth is sudden and explosive, every single time. But here's where the story gets really strange. Because the 100,000-year Ice Age cycle we've been talking about, the one driven by orbital eccentricity, the one that seems so regular and predictable, it hasn't always been the dominant pattern. Go back far enough in Earth's climate record and everything changes. 1 million years ago, Earth was freezing and thawing on a completely different schedule, not every 100,000 years, but every 41,000 years. The ice ages were shorter, less intense, and followed a different orbital rhythm entirely. Then, somewhere between 2 million and 800,000 years ago, something happened. Something that climate scientists still argue about today. The pattern shifted. The 41,000-year cycle weakened and faded. The 100,000-year cycle took over. And suddenly, Earth's ice ages became longer, deeper, and more catastrophic than anything the planet had experienced before. This shift is called the Mid-Pleistocene Transition, and it's one of the most profound climate mysteries in Earth's history. Because here's the thing, the orbital mechanics didn't change. Earth's axial tilt, its precession, its orbital eccentricity, all these cycles were operating exactly the same way 1 million years ago as they do today. Milankovitch cycles don't suddenly switch frequencies. They're driven by gravitational interactions between Earth and other planets, processes that operate on timescales of millions of years, not hundreds of thousands. So if the external forcing remained the same, why did Earth's response to that forcing change so dramatically? Why did the planet suddenly start plunging into ice ages that lasted 3 times longer and produced ice sheets twice as thick as the earlier cycles? The answer isn't simple, and the more scientists study the Mid-Pleistocene Transition, the more they realize it wasn't caused by one factor, but by a perfect storm of changes that all converged during the same geological moment. Let's start with what we know for certain. Before the transition, during what's called the early Pleistocene, Earth's climate was responding primarily to the 41,000-year obliquity cycle. This is the cycle of axial tilt variation, when Earth's axis tilts between 22.1 and 24.5 degrees. This tilt determines how extreme the seasons are, and therefore how much summer melting occurs at high latitudes. When tilt is greater, summers are warmer at the poles, ice melts more efficiently, and glaciation is harder to sustain. When tilt is lower, summers are cooler, ice persists year-round, and glaciers can grow. For millions of years, this 41,000-year rhythm dominated. Ice sheets would grow for roughly 20,000 years, then collapse and retreat during the next 20,000 years. The cycles were relatively symmetric, growth and decay taking about the same amount of time. The ice sheets never grew massive enough to cover all of Canada and extend down to New York. They were substantial, but manageable. Earth could shake them off without too much trouble. Then the transition began, gradually at first, then accelerating around 900,000 years ago. The 100,000-year eccentricity cycle started asserting itself. Ice ages began lasting longer. Instead of collapsing after 40,000 or 50,000 years, ice sheets would persist for 80,000, then 90,000, eventually reaching the full 100,000-year duration we see in recent cycles. And as they lasted longer, they grew larger. The Laurentide ice sheet over North America, which had been relatively modest during the 41,000-year cycles, began expanding southward until it reached as far as present-day Illinois and Ohio. The Scandinavian ice sheet did the same thing in Europe, grinding across the landscape like a continental-scale bulldozer. Something had changed Earth's sensitivity to orbital forcing. the planet was now capable of sustaining ice ages that its earlier climate system couldn't maintain. But what? The first and most compelling theory involves atmospheric carbon dioxide. CO2 is Earth's primary thermostat. It determines how much of the sun's energy gets trapped in the atmosphere versus radiating back to space. During the early Pleistocene, atmospheric CO2 levels seem to have fluctuated within a relatively narrow range, probably between 240 and 280 parts per million. This provided enough greenhouse warming to prevent ice ages from getting completely out of control, but ice core data, laboriously extracted from Antarctica's deep ice sheets, suggests something changed during the Mid-Pleistocene Transition. CO2 levels began dropping during glacial periods to concentrations lower than anything seen in earlier cycles. Some glacial periods saw CO2 fall to 180 parts per million, dangerously close to the minimum threshold needed to sustain plant photosynthesis. Why did CO2 start dropping so low? This is where things get complicated. Carbon dioxide in the atmosphere is part of a complex cycle involving the oceans, the land surface, and living organisms. During ice ages, several processes work to remove CO2 from the atmosphere. Cold ocean water absorbs CO2 more efficiently than warm water. Growing ice sheets lock up water, changing ocean circulation patterns. Continental shelves that were submerged during warm periods get exposed as sea levels drop, altering the biological productivity of coastal zones. But around 1 million years ago, something amplified these CO2 removal processes. One leading candidate is changes in ocean circulation. The Atlantic Meridional Overturning Circulation, that great oceanic conveyor belt that moves warm surface water northward and cold deep water southward, seems to have been restructuring itself during this period. As ice sheets grew larger, massive amounts of fresh water from melting ice would periodically flood into the North Atlantic, disrupting the normal pattern of deep water formation. When deep water formation slowed or stopped, the ocean's ability to cycle carbon changed dramatically. Carbon that would normally circulate back to the surface relatively quickly instead got trapped in the deep ocean for thousands of years. Think of it like a carbon prison. Organic matter sinking from the surface ocean would decay at depth, releasing CO2 into the water, but that CO2-rich water would just sit there in the deep ocean, not mixing back to the surface, not exchanging with the atmosphere. The result? Atmospheric CO2 levels dropped even further, amplifying the cooling that was already being driven by orbital variations. This created a feedback loop. Lower CO2 meant colder temperatures meant larger ice sheets. Larger ice sheets meant more disruption to ocean circulation. More disruption meant even more carbon getting locked in the deep ocean. The system was reinforcing itself, creating ice ages that could sustain themselves far longer than the orbital forcing alone would predict. But carbon dioxide changes can't explain everything. Because alongside the CO2 shifts, Earth's physical geography was also changing. Continental drift doesn't stop. Mountains keep growing. Ocean basins keep evolving. And during the period leading up to the Mid-Pleistocene Transition, several crucial geographical changes were reaching critical thresholds. The Tibetan Plateau, one of the largest and highest landmasses on Earth, had been steadily rising for millions of years as the Indian subcontinent slowly crashed into Asia. By 1 million years ago, it had reached elevations that fundamentally altered atmospheric circulation patterns across the entire northern hemisphere. The plateau acts like a massive stone in a stream, deflecting the jet stream, changing precipitation patterns, affecting how heat and moisture move around the planet. Some climate models suggest that the rising Tibetan Plateau strengthened the Asian monsoon system, which in turn affected how much moisture was available for ice sheet growth in Siberia and North America. More complex circulation patterns meant more variable climate, which paradoxically made it easier for ice sheets to grow during favourable orbital configurations, and harder for them to melt during unfavourable ones. Meanwhile, in Central America, the Isthmus of Panama was completing its formation, fully closing the connection between the Atlantic and Pacific Oceans around 2.7 million years ago. This closure had been gradually redirecting ocean currents, strengthening the Gulf Stream, and changing how heat was distributed around the planet. By the time of the Mid-Pleistocene Transition, these circulation changes had been operating for over 1 million years, slowly conditioning the climate system for the shift to longer ice age cycles. Then there's the regolith depletion hypothesis, which sounds technical but is actually beautifully simple. Regolith is just the layer of loose rock soil and sediment that sits on top of solid bedrock. Before the Pleistocene ice ages began, much of the northern hemisphere continents had thick regolith layers, built up over millions of years of weathering and erosion. When the first ice ages began during the early Pleistocene, advancing glaciers didn't just freeze the landscape, they scraped it. Glacial ice is like sandpaper, grinding away at whatever sits beneath it. With each 41,000-year cycle, the ice sheets would advance, scrape away a few meters of regolith, then retreat, advance, scrape, retreat, over and over again for hundreds of thousands of years. By the time of the Mid-Pleistocene Transition, vast areas of Canada, Scandinavia, and northern Russia had been scraped down to bedrock. The thick, loose regolith layers were gone, replaced by hard crystalline rock. And here's the critical detail. Ice sheets behave very differently when they sit on bedrock versus when they sit on soft sediment. Soft sediment acts like a lubricant. Ice can slide relatively easily over it, which means ice sheets can flow faster, advance quicker, and also retreat quicker when conditions change. But bedrock provides friction. Ice sheets sitting directly on hard rock move more slowly. They're more stable. They can grow thicker without collapsing under their own weight. This means that once enough regolith had been scraped away, ice sheets could sustain themselves for much longer periods. They became more resistant to the warming effects of favourable orbital configurations. A 41,000-year warming cycle that would have been sufficient to melt an ice sheet sitting on a soft sediment might barely make a dent in one sitting on bare bedrock. The ice ages got longer not just because CO2 was lower or ocean circulation had changed, but because the physical substrate beneath the ice sheets had been fundamentally transformed by previous glaciations. Earth had prepared its own prison, scraping away the very material that might have allowed quicker escape from glacial conditions. All these factors, CO2 changes, ocean circulation shifts, geographical evolution, regolith depletion, they were converging during the same geological moment. None of them alone would have been sufficient to trigger the Mid-Pleistocene Transition, but together they crossed a threshold. The climate system shifted into a new mode of operation, one capable of sustaining the massive long-duration ice ages that have characterized the last 800,000 years. But here's what really keeps climate scientists awake at night. The transition wasn't gradual, it wasn't smooth. The shift from 41,000-year cycles to 100,000-year cycles happened relatively quickly in geological terms, within a few 100,000 years, and it was marked by increasing climate variability, wild swings between glacial and interglacial conditions, periods when the system seemed to be searching for a new equilibrium. This tells us something profound and unsettling about Earth's climate. It's not a simple, linear system that responds predictably to external forcing. It's a complex network of interconnected processes with thresholds, feedbacks, and tipping points. Push it in certain ways, and it responds gradually and predictably. Push it past certain thresholds, and it can flip into entirely new states of operation. The Mid-Pleistocene Transition represents one of these state changes. For reasons we still don't completely understand, Earth's climate system crossed a threshold around 1 million years ago and reorganized itself around a new dominant frequency. The orbital forcing that had always been there suddenly started producing dramatically different results. What makes this particularly relevant today is that we're conducting our own experiment with Earth's climate system. We're changing CO2 levels faster than at any time in the geological record. We're altering ocean chemistry, changing precipitation patterns, melting ice sheets. We're pushing the system in ways it hasn't been pushed before. The Mid-Pleistocene Transition teaches us that climate systems can have tipping points, that gradual changes in forcing can produce sudden changes in response, that feedback mechanisms can amplify small perturbations into large-scale reorganizations. The early Pleistocene climate looked stable, operating on its regular 41,000-year rhythm. Then something shifted, and suddenly Earth was capable of ice ages that lasted 100,000 years and buried continents under miles of ice. Could our current climate system be approaching a similar threshold? Not toward colder conditions where warming the planet, not cooling it, but toward some other state we haven't seen before, some configuration of ocean circulation, atmospheric patterns, and ice sheet dynamics that operates according to different rules. We don't know. But the Mid-Pleistocene Transition reminds us that Earth's climate is capable of surprises, that systems that seem stable can reorganize themselves in ways that fundamentally change how the planet works, that the past 1 million years of Earth history, far from being monotonously regular, contains evidence of profound changes in how our world responds to the cosmic rhythms that govern its temperature. The shift from 41,000-year cycles to 100,000-year cycles wasn't just a curiosity. It was a warning, a demonstration that climate systems can cross thresholds and never go back, that the rules can change, and that understanding why and how those rules changed might be one of the most important scientific questions we can ask as we contemplate our own relationship with this restless, dynamic, surprising planet we call home. So here we are, right now. This moment, as you're listening to this, you're living in what geologists call the Holocene Interglacial, a warm period that began 11,700 years ago when the last ice age finally released its grip on the planet. The glaciers retreated. Sea levels rose by 400 feet. Forests spread across continents that had been frozen tundra for 100,000 years. And humans who had spent millennia huddling in refuges and clinging to survival suddenly found themselves inheriting an entire habitable planet. This is the world that made civilization possible. Every city you've ever heard of, every empire, every technological achievement, every war, every work of art, all of it happened during this single interglacial period. The pyramids, the Roman Empire, the Renaissance, the Industrial Revolution, the Internet, all of it compressed into just 11,700 years of stable, warm climate. But here's the thing that should make you pause. Typical interglacials, based on the patterns we've traced back through 800,000 years of ice core data, they last about 10,000 to 15,000 years. We're at 11,700 years right now. which means, by all natural patterns, we should be approaching the end. The astronomical cycle that brought us this warm period, the specific alignment of Earth's orbit, axial tilt, and wobble that melted the glaciers and gave us this comfortable world, it's already shifting back toward Ice Age configurations. The eccentricity cycle is in a phase of near-circular orbit, which reduces seasonal contrast. The obliquity, Earth's tilt, is in the middle of its 41,000-year cycle, declining slowly toward shallower angles that will weaken summers in the northern hemisphere. The precession cycle, that 26,000-year wobble, has northern hemisphere summers occurring at a point in Earth's orbit that's farther from the Sun. By all the rules that have governed Earth's climate for millions of years, we should be cooling, gradually at first, then accelerating. Snow should be starting to accumulate year-round in northern Canada, Scandinavia, Siberia. Ice sheets should be forming, spreading, locking up water and reflecting more sunlight, triggering the feedback loops that have plunged Earth into glaciation dozens of times before. But we're not cooling, we're warming, and not just a little. Global temperatures have increased by about 1–2 degrees Celsius since the late 1800s, with most of that warming happening in just the last 50 years. Arctic sea ice is disappearing at rates that would have seemed impossible a generation ago. Glaciers that have existed for thousands of years are melting away in decades. Sea levels are rising, not falling as they should be if we were sliding into a new ice age. The reason is obvious. Humans, specifically the 45 billion tons of carbon dioxide we're pumping into the atmosphere every single year. That's over 1 million tons per hour, a geological force operating at breakneck speed. We've increased atmospheric CO2 from about 280 parts per million before the Industrial Revolution to over 420 parts per million today. That's higher than it's been for at least 3 million years, possibly much longer. And here's where things get really wild. That CO2 doesn't just make things warmer in the short term, it completely disrupts the Milankovitch cycles. Remember how ice ages start? Weak summers in the northern hemisphere fail to melt the previous winter's snow. That accumulated snow becomes glaciers. Those glaciers reflect sunlight, cooling the planet further, triggering more ice formation. It's a cascade effect that depends on that initial failure of summer to melt winter snow. But increased CO2 supercharges summer temperatures. Even with weaker solar forcing from unfavorable orbital configurations, greenhouse gases trap enough heat to melt snow that would otherwise accumulate. The feedback loop that should be starting, the one that's plunged Earth into ice ages dozens of times, it's being blocked. The trigger mechanism is jammed. Scientists have run the models. They've looked at the Milankovitch cycles for the next 100,000 years, calculated the orbital forcing, factored in the CO2 we've already emitted and what we're likely to emit in the coming decades. The results are startling. Under natural conditions with pre-industrial CO2 levels, Earth probably would have entered a new glaciation period within the next few thousand years. Not tomorrow, not even in the next century, but soon by geological standards. The orbital configuration isn't quite right yet, but it's trending that way. But with current CO2 levels, the next ice age is delayed by at least 50,000 years, possibly 100,000 years or more. Humans have done something unprecedented in Earth's history. We've disrupted a planetary climate cycle that's operated with clockwork regularity for millions of years. We've taken control of the thermostat. This is what scientists mean when they talk about the Anthropocene, the age of humans. A proposed new geological epoch defined not by natural processes, but by human impact on the planet. Future geologists, if they exist, will be able to see our era in the rock record. a thin layer marking the moment when a single species gained the power to alter global climate, reshape ecosystems, and fundamentally change the planet's trajectory. And look, there's a certain perspective from which this could seem like a good thing. Ice ages are brutal. The last one displaced entire human populations, created megadroughts, caused mass extinctions of large mammals. If we've prevented the next ice age, haven't we saved future generations from catastrophe? Aren't we protecting humanity from a frozen future that would make most of the northern hemisphere uninhabitable? But here's what that perspective misses. The climate stability of the Holocene, this interglacial period we're living in, it's not just important because it's warm. It's important because it's stable and predictable. For 11,000 years, sea levels has been roughly constant. Rainfall patterns have been reliable enough to support agriculture. Temperature ranges have stayed within bounds that allowed civilizations to flourish. That stability is what let humans develop everything we think of as civilization. What we're doing now isn't creating a new stable warm period. We're creating chaos. Rapid, unpredictable change happening too fast for ecosystems to adapt, too fast for human societies to adjust their infrastructure and food systems. We're not preventing an ice age. We're creating something Earth hasn't seen in millions of years. A hothouse period with CO2 levels and warming rates that have no recent analogue. The Milankovitch cycles predict weak orbital forcing for the next 50,000 years. That means the natural astronomical factors that would normally drive climate change, they're in a relatively neutral configuration. Under normal circumstances, this would be a period of gradual, manageable cooling. Instead, we're forcing rapid warming into a system that should be stable or gently cooling. Think about what this means. The Ice Age cycle that we've spent this entire video explaining, the 100,000-year pattern that's been Earth's dominant climate rhythm for the last million years, we've broken it. We've become a geological force more powerful than orbital mechanics, at least on timescales of tens of thousands of years. But here's the perspective that really matters. We haven't stopped the cycle permanently. We've just disrupted one cycle, maybe two. The Milankovitch variations will continue. Earth's orbit will keep changing. Obliquity will keep oscillating. Precession will keep wobbling. These are driven by the gravitational pull of other planets, by the physics of celestial mechanics. They don't care about human CO2 emissions. Eventually, in a few 100,000 years, there will be another interglacial period like ours. And if humans or whatever species evolves from us are still around, they'll face the same question we're facing now. What happens when the astronomical configuration shifts back toward glaciation? Will the CO2 we've emitted still be in the atmosphere, still blocking ice formation? Or will it have been gradually absorbed by weathering, ocean processes, and geological sequestration, allowing the natural cycle to resume? The models suggest our CO2 pulse will last a long time by human standards. Even if we stopped all emissions tomorrow, atmospheric CO2 would take thousands of years to return to pre-industrial levels through natural processes. The excess heat we've added to the oceans will persist for centuries. We've committed the planet to a warmer trajectory for longer than recorded human history. But on geological timescales, even this massive human impact is temporary. Earth has been through worse. The Permian Triassic extinction 252 million years ago, the Great Dying, saw volcanic eruptions pump out enough CO2 to raise global temperatures by 10 to 15 degrees Celsius. Ocean acidification killed 96% of marine species. It was apocalyptic by any measure, yet Earth recovered. New species evolved, life continued. Within a few million years, the planet had restored balance. The Paleocene-Eocene thermal maximum 56 million years ago saw a massive pulse of greenhouse gases, possibly from volcanic activity or methane release from ocean sediments, raise global temperatures by 5 to 8 degrees Celsius. Forests grew in the Arctic. Crocodiles lived at the poles. It lasted about 100,000 years. Then it ended. Carbon was sequestered. Temperatures normalized. The planet found a new equilibrium. Earth is resilient on geological timescales. The question isn't whether the planet will survive human activity. It will. The question is whether human civilization will survive the consequences of disrupting systems we depend on. Because here's the hard truth. We live on human timescales, not geological ones. We care about the next century, maybe the next millennium. We need stable coastlines, predictable weather patterns, consistent agricultural zones. We've built trillions of dollars of infrastructure based on assumptions about where the ocean will be, where rain will fall, what temperatures we'll experience. All of that is now in flux. Sea level rise that's already locked in from the warming we've caused will displace hundreds of millions of people. Rainfall patterns are shifting, turning bread baskets into dust bowls and vice versa. Temperature extremes are becoming more common, stressing electrical grids, water supplies, human health. And the Ice Age cycle we've disrupted. It was part of a larger climate system that included predictable patterns of atmospheric circulation, ocean currents, biome distribution. By injecting chaos into one part of that system, we're destabilizing all of it. So where do we stand in the cycle? We're in a period that should, by all natural patterns, be the late stages of an interglacial. We should be savoring the last few thousand years of stable warmth before the slow descent into glaciation. Instead, we're forcing the system in the opposite direction, creating a super interglacial, a period of warmth that's breaking all the rules. Could we prevent the next ice age entirely? Probably not permanently, but we might be able to delay it indefinitely on human-relevant timescales. If we maintain high CO2 levels for thousands of years, we could keep the planet warm through multiple Milankovitch cycles that would otherwise trigger glaciation. We'd be choosing warmth over the natural rhythm of ice and fire that's governed Earth for millions of years. But that's a big if. Maintaining current CO2 levels would require continuing to burn fossil fuels for millennia, or it would require some future civilization actively choosing to prevent glaciation by releasing greenhouse gases. More likely, human CO2 emissions will peak sometime this century and then gradually decline as we shift to renewable energy or exhaust easily accessible fossil fuels. In that scenario, atmospheric CO2 would slowly decline through natural processes. In 10,000 years, maybe 20,000, levels might be low enough that the Milankovitch cycles could resume their influence. The next strong orbital configuration favoring glaciation might find a planet that's ready to respond, and the ice would return. The ultimate fate of Earth's climate, over the next millions of years, is almost certainly more ice ages. The conditions that created the Pleistocene Ice Age cycle, the positions of continents, the configuration of ocean currents, the presence of large land masses at high northern latitudes, those aren't changing anytime soon. As long as those factors persist, and they'll persist for many millions of years, the Milankovitch cycles will continue to drive climate variation. There will be more 100,000-year glacial periods, more brief interglacials, more cycles of ice sheet growth and retreat. The pattern will continue long after humans are gone, long after whatever we build has crumbled to dust, long after the last trace of our CO2 pulse has been absorbed by the slow, patient processes of geological weathering. Eventually, hundreds of millions of years from now, Continental drift will change the game. Continents will move into different configurations. Ocean currents will shift. The conditions that make ice ages possible might disappear. But that's so far in the future that it's almost meaningless to contemplate from a human perspective. For now, we're living in the strange transition period, the interglacial that should be ending but isn't, the warm period that we've extended artificially, buying ourselves time that the astronomical cycle never intended to give us. We're experiencing the planet between ice ages, but we've jammed the door to the next one, at least temporarily. And that's where we stand, in a world out of sync with its natural rhythms, a planet that's confused, receiving contradictory signals from its astronomical pacemaker and its newest, most unpredictable variable industrial civilization. We're living in the pause between the end of natural climate and the beginning of whatever comes next, a future we're writing in real time for better or worse. The ice ages will return, that's almost certain. The cosmic dance will continue. But when they return, and what the planet looks like when they do, that depends on choices we're making right now. We've become part of the cycle, a force within the system that shaped Earth's climate for millions of years. We didn't ask for that responsibility, but we have it anyway. So here we are, after journeying through nearly 1 million years of Earth's frozen cycles, after exploring the cosmic mechanics that govern our planet's climate, after witnessing the ice sheets advance and retreat like breathing lungs across continents, we arrive at a simple, beautiful truth. Earth freezes every 100,000 years because the universe runs on rhythms we can barely comprehend. Think about what we've discovered. 3 orbital variations, eccentricity, obliquity, and precession, each operating on its own timescale, each adding its voice to a cosmic symphony that's been playing for millions of years, the 100,000-year stretch and squeeze of Earth's orbit, the 41,000-year wobble of our axial tilt, the 26,000-year circular dance of our rotational axis. Separately, these movements seem random, chaotic, impossible to predict. But together they create a pattern so precise you could set your watch by it. If your watch measured time in tens of thousands of years, the mathematical elegance of it is almost overwhelming. Changes in sunlight reaching high northern latitudes of less than 1%. Variations so subtle that if you were standing there, you'd never notice them from one year to the next. Yet these whisper-quiet shifts trigger feedback loops powerful enough to bury New York City under 2 miles of ice, to drain the oceans by 400 feet, to transform the entire face of the planet for 6 million years this pattern has dominated Earth's climate. The ice advances when the orbital dance reaches certain configurations. It retreats when the dance shifts again. With clockwork precision the glaciers march south, pause for millennia, then melt away in geological instants. Over and over, 26 times during the past 6 million years alone. Each cycle reshaping landscapes, redirecting rivers, creating lakes and destroying them, carving valleys that would become the homes of future civilizations, and the truly humbling part. This has been happening long before humans existed, long before mammals walked the earth, long before dinosaurs ruled. The Milankovitch cycles have been operating for the entire 4.5 billion year history of our planet, patiently cycling through their cosmic choreography, indifferent to whatever life might be watching from the surface below. Our species, Homo sapiens, has existed for maybe 300,000 years. We've been behaviourally modern for perhaps 70,000. We've had agriculture for 10,000 years, civilization for 5,000. The entire span of recorded human history, every empire that's risen and fallen, every war fought and peace treaty signed, every technological revolution from the wheel to the smartphone, all of it has occurred during a single interglacial period. One brief warm pause between ice ages. We are living in the cosmic equivalent of a summer afternoon. Comfortable, warm, stable. Perfect for developing agriculture, building cities, creating the complex societies that define human civilization. But summer always ends. The orbital mechanics don't care about our cities or our civilizations. They're already preparing the next act. In about 50,000 years, maybe sooner, maybe later, the orbital configurations will shift again. The ice will return. Glaciers will advance from the poles. Sea levels will drop. The patterns that have governed Earth for millions of years will continue doing what they've always done, and our distant descendants, if they're still around, will have to adapt just like every other species that survived these cycles before. But here's what's remarkable. We're the first species in Earth's history that actually understands this pattern. We're the first to predict when the ice will return. We're the first to look at the geological record and see not chaos but order, not randomness but rhythm. We've decoded the clockwork mechanism of planetary climate. We've traced the invisible hands that wind Earth's climate clock. That knowledge carries responsibility. Right now, we're adding our own influence to these ancient cycles. Human activity is pumping greenhouse gases into the atmosphere at rates the planet hasn't seen in millions of years. We're running an uncontrolled experiment on the same climate system that's been operating with such precision for so long. The orbital cycles will continue regardless. They're far too powerful for humans to influence. But we're definitely affecting what happens between the cycles in these precious interglacial periods when civilization becomes possible. The Ice Age cycle teaches us something profound about perspective. We think in human timescales, years and decades, maybe centuries if we're historically minded. But Earth thinks in epochs. The planet measures time in ice sheets and orbital cycles. What seems permanent to us, coastlines, climate zones, the distribution of land and sea, is temporary in Earth's accounting. Everything flows. Everything changes. The only constant is the rhythm itself. So as you drift off to sleep tonight, take comfort in this. Earth has survived far worse than anything we can imagine. It's weathered countless ice ages. It's adapted to orbital variations for billions of years. The same forces that built the Himalayas and carved the Grand Canyon are still at work. Patient, persistent, unstoppable. Our planet is resilient in ways that make human concern seem fleeting. If you've enjoyed this journey through Earth's frozen cycles, hit that like button. Drop a comment telling us where in the world you're listening from, and subscribe for more deep dives into the patterns that shape our universe. The Ice Age cycle is just one of countless rhythms that govern existence. There are so many more stories to tell. The cosmic dance continues, the orbital variations keep cycling, and somewhere in the distant future, the ice will return, right on schedule as it always has, as it always will. Sweet dreams.